Today we're going to be looking at a couple more clues that Mother Nature gives us regarding opacity and transparency. We covered two of them, okay? And so let me review that real quick, okay? The first one is that I'm saying that if you misalign something, there's a tendency for it to become opaque, okay? And the proof, the evidence, the thing that convinces people usually is some kind of evidence. All I'm showing is one example that Mother Nature has, and that's polarization. And here we did an experiment, okay? And you can see that when the two lenses are aligned, the laser goes through. When you misalign them, you put one at 90 degrees to the other, the laser does not go through. So in one case, we have transparency. It goes through. Someone called it translucent, and I don't use the word translucent because it essentially means the same thing as transparency. There's very little difference, just a matter of degrees and dispersion. So I'm just going black and white here. I'm saying transparent and opaque, opacity, right? And here you can see that it's opaque in one direction. You can't see. If you had your eyes on that board there on the back, you would not be able to see the light. Whereas if we turn it like it is now, then you would see the light. So yes, just by modifying the location of the atoms of the molecules that comprise these two lenses, we can make something opaque and transparent without anything else. Okay, so that's what I showed there. How do we explain it under the rope model? Or here I showed it. Again, I'm not going to go in detail because I've covered this in the last couple sessions. Again, here it is. I'm saying that if those are the atoms, the molecules that build up the lenses, and I'm using the example of calcium or carbonate, the ropes are lined straight ahead, and both lenses are aligned. All the atoms are facing in the same direction on both lenses. Once we turn one of them sideways, and here I'm going to show that, okay, what happens, the same ropes are no longer connected straight ahead. Okay, that's one of the mechanisms that I'm proposing, okay? And again, this is a proposal for you to ponder, for you to think about. People say, have you proved it? No, we don't prove in science. So we just explain the mechanism so that you understand it. You reach your own conclusions if that's possible or not, if what I just explained is possible or not. The other one is, again, you have the rope, and we're going to turn one of the polarizers, the one in the back. We're going to say this fist here, this one here, is one of the polarizers, one of the atoms of the polarizer. Here's another atom. And if you turn it just 90 degrees, you can see what's happening. The length of the links, it changes. Okay, so it's not the same here as it is here. Okay, that's another thing that happens when you rotate one of the polarizers. Okay, so those two things are things that you got to keep in mind when you're analyzing the alignment of molecules. And so the question is, would you be able to see through a brick wall, if God, waved his magic wand and made all the atoms or molecules of the brick be aligned? If they were all aligned, would you be able to see a light coming from the other side of the wall, for example? Okay, so that's for you to think, for you to ponder, okay? And some people have problems with that, and again, it's because they're tied to the 19th century. They're still living in the 19th century. Here it is. Fellow says, polarization has absolutely nothing to do with materials being transparent. I covered that the other day. We just look at the definitions of transparent and opaque, and we find out that that's exactly what transparent and opaque mean. It's does light go through or not, okay? And that's the quantum version, okay? So yeah, polarization either allows the light to go through using quantum version, right? Or it doesn't. And so, yeah, polarization does have a lot to do with this subject matter that I'm talking about, which is opacity and transparency. Okay, another issue that was raised by another fella says, let us try one more time, okay? Says, water molecules in, for example, swimming pool are not aligned, and yet water is highly transparent. What gives? Okay, and here we see another fellow who says, so the idea is that transparency has something to do with molecular alignment? I don't know, Bill. I think that the other guy who mentioned water molecules is right. He's referring to the guy on the left. Okay, and then he adds to that, he says, glass, which has disordered amorphous molecular structure, is about as transparent as quartz, chemically the same but structured crystalline aligned. Okay, if light is torsional, couldn't it be more of a matter of stiffness? Example, metal is reflective because it is too stiff to relay the torsion. Okay, so what do we answer these gentlemen? Okay, let's go with the first one. Okay, and it goes like this. I'm going to try it one more time as well. Alignment is not the only mechanism Mother Nature uses to do transparency. Let me repeat that because they haven't heard yet. Alignment is not the only mechanism. I'm trying to go through the different mechanisms. I covered one, and they already said, oh, but the water molecules aren't aligned. I never said that they did. They were aligned, and that's the reason water is transparent or air is transparent. I suggested that one of the mechanisms Mother Nature uses is alignment. Okay, so this is, keep in mind the context here. Okay, we're saying that one of the mechanisms is alignment. The second issue is, are water molecules in a swimming pool aligned or not? Because these people take for granted that water is not aligned. They say, oh, water molecules move in every which way. And so the question is, do water molecules rotate 90 degrees when you tilt the glass of water? Yes or no? If we leave the water for a long time, just sitting there, right? 3 days, whatever you want, and allow it to settle down, will all the molecules be facing in the same direction due to gravity? Okay, these are the questions before you. Okay, these are questions. Okay, the question is whether we have an answer to them or not. And right now, all I'm doing is asking the question because these people take for granted that molecules are not aligned. Water and air molecules are not aligned. They imagine all these molecules just going in all different directions because that's what they learned in high school or college. Is that the case? So let's go one more time over it so that you understand what the issue is, what the question is. Right now, you don't even understand the question. Okay, so let's go with the question, with what the issues are. Here's the experiment we did with Hans, my son. We turned water around. Okay, we had it horizontal, and now we turned it vertically, right? Never do this except in the presence of a relativist, okay? So when we turned the water around, did the water molecules, the individual water molecules there, the gazillions of water molecules, did they also turn around 90 degrees, or did they remain in the same direction with respect to the center of the earth? That's the question before you. Let's continue so that everybody understands what the question. Right now, these people are not even understanding the question. Okay, I need to make sure people understand what the question, what the issues are. Okay, here we have a water molecule. We have 2 hydrogen, 1 oxygen. Okay, and I put it facing in that direction arbitrarily. Okay, this is arbitrary. I'm just putting it in that direction. Why did I choose that specific direction? Okay, here is why I chose that direction. The oxygen has 8 ropes connected to any atom in the universe, whereas the hydrogens only have 1 rope. Why is that? Because every element in the periodic table is simply an agglomeration or just a bunch of hydrogen atoms. So uranium, for example, has 92 atoms. What are we talking about? We're saying it's got 92 hydrogen atoms in it, essentially. It's got some neutrons as well, but we're not going to talk about that right now. I'm just saying that what we have is at least 92 hydrogen atoms in a uranium atom. And so here we have oxygen's element number 8. And so, yeah, it's got 8 ropes. It's got 8 hydrogen atoms. That's why I put it in that direction. It's, again, arbitrary, but I just put it in that direction to make a point. What's the point that I'm trying to make? Let's see if these people understand what the issues are. Okay? Here's the issue. The issue is when you turn water around, does the water molecule also turn around and stand on its head? Or does it remain pointing in the same direction as the one on the left? Okay, that's the issue before you. Okay? And here we have the whole bunch of atoms, or molecules really in this case, okay, water molecules. And you can see what's happening to them. We turn them around, and the question is, does the water molecule also turn on its side, or does it remain like the one on the left, always pointing in the same direction when you turn the glass around? Okay? And I don't know if I'm getting through to these people, but hopefully intelligent people can understand what I'm saying. I'm saying, does the water molecule stand on its head, or on its side, or however you want to see that? Okay, and here's another analogy, okay, so that maybe some of these people might be able to pick up on that. Here you have all these dummies, soccer dummies that they use to practice, and you can push it on the side, but then it comes back to its original position. So maybe when we turn the glass around, sideways, it could be that momentarily, because of friction, the molecules momentarily move in some direction, okay? But then do they come back to their normal position, which is pointing in the same direction with respect to the center of the earth? And people say, no, they're all jumbled up. They're all moving around in different directions. Are they? Have we ever seen an oxygen molecule, meaning, air, O2, okay? Have we ever seen any water molecule? No, we have not. We cannot see an atom, especially a hydrogen atom. Okay, we cannot see it. With the most powerful microscope that you can imagine, we cannot see a hydrogen atom. We've never seen a hydrogen atom. That's why the quantum mechanics have no idea what a hydrogen atom looks like. They can't draw one for you. They say it's a little ball with a little electron bead going around it, and you say, okay, can you show me the photograph that you took of that? And no, they cannot, because the model is ridiculous. You cannot explain why that electron bead doesn't fly away automatically, on its own, or fall to the nucleus. So they use that model because they have to explain ionization, electricity, and who knows what else, quantum jump. But it's an irrational model because they cannot explain, again, why that electron bead stays faithful to that proton, in the center, proton bowling ball, as I call it. Okay, so this is the issue. And so the question is, if they have never seen a hydrogen atom and they have never seen a water molecule, one water molecule, when you turn the glass around, did the water molecules turn on their side? Maybe you shook them a little bit because they're all touching against each other, and one's at the edge, touch the edge of the glass. Okay, you got to consider all these things there. But then the question is, is that just a quick momentarily thing that happened, like with a dummy, the soccer dummies? You push them down, momentarily it's down, but immediately it stands up. Okay, all by itself. Why? Because it's pointed towards, the gravity is pointed towards the ground, towards the center of the earth. So this is what the issues are. Okay. So it's for you to ponder. Okay, you got to think. This is food for thought. Okay, I hope people are understanding some of this. Okay, what's the second mechanism that we covered? Here it is. Okay, and it's the one that quantum mechanics says. It says that if a photon comes in and hits an electron, it compels it to jump to a new energy level. When that happens, only when it happens, if the photon has enough energy to push it up there, then the electron bead, the photon bead is absorbed and it doesn't reach your eyes, and the material is opaque. But if for some reason the electron ball, the purple one there, does not absorb that photon, then the photon reaches your eye and the material is transparent. That's essentially it's a little more involved than that. I'm just reviewing it very quickly. So if it absorbs it, it doesn't reach your eye. If it doesn't absorb it, it reaches your eye. That's the difference between opaque and transparent, according to quantum mechanics. One of the arguments out there, probably the most important one. Okay, and so the issue here is that we showed the other day that if you put one layer of plastic there that I put, you can see the light in a candle. But when you put many layers, like I do here, you can't see that light at all. And so the question is, what prevented the light from reaching my eyes if all I did was put more layers of that plastic? I mean, shouldn't the photon still go through all those atoms that are between my eye and the candle, and because none of them are absorbed? In other words, the photon would have to pick up more and more energy as it goes along until it's finally absorbed by by one of the atoms of those layers of plastic, and then it doesn't reach my eye. And so how did the photon gain more and more energy to finally be able to hit an electron and knock it to a higher energy level? That's the question before you. Okay, so what I'm showing with this is that you cannot use that mechanism to explain what we're seeing there. Okay, if we put more layers of something, in this case it was this plastic, okay, and if you put more and more layers of this, that's all I did, just put more layers. At some point, you can't see the candle, the light. It's light, I can't see the light anymore. It's just a matter of how many layers I put in there. And if quantum is right, and it's all about the photon being absorbed by an electron, meaning the electron has to have sufficient energy to knock it to the higher energy level. If it has that, then it's absorbed. And so are we saying that by putting more layers, the photon gained more and more energy, that at some point it was able to knock an electron to the higher energy level? Is that what these people are saying? Obviously, that's nonsense. It's poppycock. Okay, so you cannot explain it with that mechanism that quantum mechanics has. Okay, a couple fellas insist. Okay, so microwaves does go through walls. My Wi-Fi works through walls. Okay, and so he says these waves, whatever they are, they go through his walls. Very scary stuff. And the other fellow says light goes through transparent materials. Okay, so here's a material, a wall, and he says it goes through it. I guess he's talking about particles or waves, maybe like the previous guy. Is that's what's happening? Is it going through? And the first problem with this is what I showed the other day. And so these people haven't listened, so I'm going to put it again. I'm sorry I have to do this for those people who are intelligent, but these people are obviously not very smart, okay? Because they're insisting on something that cannot be. They talk about going through, traveling through. And what they're referring is to this, to particles or waves. Well, the particles, especially the quantum particles, are not particles. They're not corpuscles. They're not beads. So you can't use the word particle to give a physical interpretation for transparency or opacity. And transverse waves are not physical objects. What you're staring at there is what? You're staring at vectors. What you're seeing is those blue and red arrows. They're vectors. They're mathematical vectors. A vector is magnitude and direction. That's what the arrow stands for. They've got these things moving, and people think they're looking at, oh, I know what I'm staring at. I'm staring at a wave. No, there is no physical object called a wave. And there is no physical object in quantum called a particle. Okay, so once you understand that, you cannot use this term going through or traveling through like these two gentlemen are talking about here. You can't use waves, and you can't use the quantum particle, so-called particle. So the question is, what is going through? They claim that waves and or particles, right, are going through their walls. And so first you got to tell me what it is that's going through your walls. You got to tell me what physical object we have there. That's the first one. Don't say that waves go through my wall or light particles go through my wall. Tell me what those particles are. Okay? And then tell me by what mechanism they go through your wall. Again, can you shoot a bullet? In fact, a bullet. Can you shoot a bullet through the wall? More than likely it'll get smashed into the wall and it'll stay there. It won't go through the wall as if the wall weren't there. The wall is not transparent to bullets. And why would the photon go through a wall in the same way? We have a little bullet there that's going through the wall. What is going through the wall? What physical object? You have to identify the physical object before you even talk about going through. Okay? And so that's the task that these people have. Under the rope model, it doesn't go through. What we have is relaying. What you have is two atoms, one atom from source connected to the wall, and then the wall atom is connected to another atom behind it. And in some cases it goes through and it's transparent. In some cases it doesn't go through and it's opaque. And we're covering those mechanisms that Mother Nature uses. Okay? And so all I'm saying, this is the mechanism we have. It doesn't go through. Light doesn't go through anything. Light simply is relayed from atom to atom, whether it's a wall or whether it's glass, air, or water. It doesn't matter. It's always relayed from atom to atom. Okay, this is a new mechanism that we're proposing. Okay, again, food for thought for people who have an open mind and can analyze these situations. Okay, another fella. Today was question driven because they were all pertinent. Okay, so here another fellow says, I didn't understand the part about reflection not occurring at the surface of the water. Okay, I saw a reflection both on the surface and at the bottom where the mirror was. I showed an experiment where I have a mirror at the bottom of a trash can and I filled it with water, and I showed that I can always see the mirror with water and without water. So I'm seeing all the way through the water all the way to the bottom. And so this person is questioning that. He says, well, I thought a reflection is from, like most people think, is from the top of the water, from the surface of the water. And what they're thinking about is this. Good old Narcissus, they say, well, when I look at the water, I can see my reflection. Is that reflection coming from the deep ocean, from the sand at the bottom of the ocean, or is it coming from the surface of the water? And what we're talking about is two different things here. The one on the left, we're saying, look, if you drop a coin, or in this case a shoe, like I showed there, at the bottom of the pool, okay, why can you see the shoe? I'm not talking about you looking at your face in the surface of the water. I'm talking about seeing the shoe that's at the bottom of the pool. And what you have to answer is, how did the light from the shoe get to the surface of the water? That's the question before you. How is it that I can see that shoe, which is at the bottom of the pool, okay? Am I just looking at the reflection at the surface? And if so, fine. I'll accept that. And then you have to tell me how that light got from the shoe at the bottom, the real shoe at the bottom of the pool, all the way to the surface. Okay, so that's what you got to explain. So if you drop a coin somewhere, in the fountain of youth, okay, why can you see the coin? And you can say, well, I can see my reflection at the surface. Yeah, but how come you can see the coin, which is at the bottom of the pool? That's the situation that you got to answer. That's the question before you. Okay, another fellow says, two-way mirrors have coating. Actually, it's a one-way mirror. Okay, one direction it's a mirror, and the other direction it's glass. You can see through. Okay, as you can see here, Mr. Bean, he's in front there. He sees a mirror. What do the people on the other side see? Well, they see him doing all this fancy stuff. Okay, so the question is, if I have a laser, if Mr. Bean has a laser and then points it at the mirror, he's going to get a reflection. It's going to come back to him. It's not going to go through. On the other hand, the other folks, send the laser. He's going to receive the laser on the other side or not. Okay, and so the question is, the laser goes in one direction, but not in another direction. Okay, this is the issue. And it's the same material, no matter what. Here they can see him, he cannot see them. In one direction it's transparent, in the other one it's not. It's opaque. Being mirror, we'll call that opaque. Okay, so the issue is, light goes in one direction and not in the other direction, and it's always the same mirror, the same material, the same atoms, the same molecules. Okay, so the question is, if quantum is correct, why didn't the electron absorb it in one direction? Why did it allow it to pass in another direction? Okay, so this is the issue before you. Okay, and again, I'm highlighting all these issues because these people have very short attention spans and they do not understand what's in front of them. They're so brainwashed by what they learned in high school and college, and they got a mumble jumble in their head, and they come up with all these questions. They're not listening. They're not even paying attention to what they're staring at. Okay, so again, you have a one-way mirror. The mirror is so thick, I don't care if it's coated or not coated, it's irrelevant. Light goes in one direction, it doesn't go in the other direction. It's always the same material between the two lasers. Okay, so how does quantum explain it? Electrons absorb photons, is that how quantum explains it? Okay, so this is the issue before you. Okay, today we're going to go through the third mechanism that I'm going to propose, okay, related to opacity and transparency. And it's got to do with temperature, okay? And here it is, okay? If you take argon, okay, and you take argon which is solid or argon that is liquid, either one of those are transparent. And again, I'm not going to use the word translucent. We're going to use the word transparent. We're just going to say that light goes through it, according to quantum, okay? According to rope, we have relaying of light. According to quantum, light is going through this and reaching your eyes so that you can see what's behind the glass, the liquid argon or the solid argon. Okay, but what happens if we heat it up? In fact, normal state of argon is this one, the one you're going to see, and that's argon gas. When you have argon gas, it becomes opaque. It has this violet color. No longer is transparent. Okay, and so the question is, how did all we did was change the temperature, and suddenly we go from opaque to transparent, or from transparent to opaque, just by changing temperature. Obviously, something is happening with the temperature. Okay, so temperature is another clue, I guess you could say, that Mother Nature gives us on how she plays around with transparency and opacity. Okay, so that's the point I'm trying to make. Let me show you another magic trick Mother Nature does. Okay, keep these in mind so that you can factor them into your own theories, into your own conclusions. Okay, and here it is. We have liquid oxygen, and suddenly, oxygen out there here in the air is transparent. So is nitrogen. I mean, 80% of the air we breathe is said to be nitrogen. Okay, about 19% is oxygen. Okay, and so both of them are transparent. But when you freeze, you start freezing oxygen. It turns into this bluish color, and it's no longer transparent. And all we did was change the temperature. Okay, so you got air, and you can't see it. Somehow you are able to freeze it to a certain temperature, and it becomes opaque, becomes blue like that. It's no longer transparent. Okay, we got that. Temperature seems to affect argon. Temperature seems to affect oxygen. Also affects nitrogen. You look at liquid nitrogen and so on, you'll see some difference than the nitrogen that you breathe every day. Okay. And here's another picture of that, liquid oxygen and solid oxygen. You can see it's turning somewhat bluish, okay? And you can see it's no longer transparent. And all you did was change the temperature, okay? So the question is, what does temperature do to objects that suddenly converts them into transparent or opaque, depending on which way you go with the temperature? Something's happening with this thing we call temperature, okay? Something's going on. Okay, and so this is another clue that Mother Nature gives us. Here it's opaque, same material, now different temperature. Now it's transparent. I hope that sunk in somebody's head out there. Okay, so I ran an experiment. Okay, a very dangerous experiment. Always do it in the presence of a trained relativist, okay? This is a very expensive experiment. I'm not sure if all of you can afford it, okay? So it may be out of your budget, okay? What I did was I took a little pen and stuck it into a glass and froze the glass in my freezer. Okay, so what happened? I did a time lapse of this glass, and you can see what happens. It melts, and suddenly the pen comes into view. Okay, I took different photographs like every 20, 30 minutes, so it's not perfectly stable, but it doesn't matter. I guess you get my point. Point is that the guy on the left is opaque. The one on the right is transparent. We did this with temperature alone. It's the same material. It's the same water. I didn't change the water. All I did was melt whatever was in there, which was ice. And you can see the pen comes into view. Suddenly, what was opaque became transparent. Okay, we did this only with temperature. Okay, so what happened? How do we explain this? What's going on here? You mean there's this thing called temperature, whatever temperature is, that suddenly turns materials from opaque to transparent, transparent to opaque, depending on which way you go with the so-called temperature. Okay, so here's an example of how quantum mechanics explains it versus how the rope model explains it, okay? And you can see here, this is from my book, Why God Doesn't Exist, okay? And you can see quantum water, they have these things they call hydrogen bonds. Okay, hydrogen bonds. And water is somehow, these hydrogen bonds are flexible or loose or whatever you want to call it. And when you freeze the thing, these become like sticks. You have this crystal structure suddenly in the water, turned into ice, so now these connections, whatever you want to call these hydrogen bonds, turn into solid things and they're straight and, not even Samson can break them, okay? Under the rope model, it's the rope. All atoms are interconnected by ropes. What we're saying is the rope suddenly becomes, in other words, has less frequency. It has longer longer links, okay? So we call it link length. It stands for the wavelength of quantum mechanics. And so at some point when that rope has such long lengths, it's frozen. What is heat? Heat is higher frequency, shorter links, and that's what we're going to call heat. And so that's the difference between water and ice. But we have a physical object. The physical object is the rope. That's the one that's either gaining heat or losing heat, meaning gaining frequency or losing frequency, right? And with that, we can explain, what the hydrogen bond is. What is the hydrogen bond according to quantum mechanics? Well, here it is. This is the hydrogen bond. Okay, this is from the Wikipedia, and there's a comment there. The last paragraph comes from another site. It says, what is a hydrogen bond? Well, it's an electrostatic what? Force. What is a force? Is a force a physical object? Can you draw a picture of a force? Can you bring it to me and say this is a force? No, force is a concept. You can't say that it's an electrostatic force. Is that what you're going to freeze? An electrostatic force? This is what quantum is saying, okay? Force of attraction between a hydrogen atom and another atom. So they're saying they're freezing a force. What sense does that make? It's like saying, I froze love. I froze time. I froze intelligence. That's what I think they froze, okay? The hydrogen bond can be viewed as a metric-dependent electrostatic scalar what? Field. Is a field a physical object? Is there a physical object? You can bring a magnetic field and put it in the center of the conference room without the magnet, obviously. Maybe you can bring a gravitational field and put it in the center and show if this is a field. And if you don't bring it in, can you draw it? What are you going to draw for a field? Field is defined as values at each point in space. That's what a field is. It's a concept, a mathematical concept. So for them to say that a hydrogen bond is a field of any kind that does whatever it wants to do is nonsense. A bond, a thing, right? They're talking about a stick because they're drawing it as a stick, cannot be a force or a field. There's no such physical object as force or field in science or physics, okay? And then they explain, this is another side, says, during freezing, water molecules lose energy, whatever that is. I mean, what is energy? Can you bring energy and put that in a conference room, in the center of the conference room, so that we can see it from all around? Oh, that's energy. I see what it is. What is it? Some kind of smoke? Is it a gas? What is this energy thingy? Okay, this is what you got to explain. Okay? Lose energy and do not vibrate or move around as vigorously. Okay, so so the water molecule doesn't vibrate as much. Great. and they lose energy, whatever that is. Energy is a mathematical concept, so they lose this mathematical concept. What sense does that make from a physical interpretation point of view? Absolutely none. This allows more stable hydrogen bonds to form between water molecules. And again, it has to do with my explanation here. When they say they lose energy, what we're saying is that the frequency changed, which is the one on the bottom there, along the rope. What does that mean? Well, it means that the links become longer. And the longer they become, the colder they are, the frequency is lower. And what you have is long links. Okay, so let's get rid of these so that you can see here. Give me a second here. Get rid of these two. This is what I'm saying. Here we have a rope, okay? And what we're saying is this is heat, high frequency, short links. As you unwind the rope, it gets colder. The links become longer, the frequency is less. Okay? That's what we're saying. There's fewer links. And the more you untorque it, the colder it is. That's what coldness is under the rope model. And yeah, now you have a stick. And that's what the hydrogen bond is. Okay, it's a stick. It's a stick made of something. Hopefully there's something there. Otherwise you're putting black magic spirits in that space. You're saying that between two atoms, there's a hydrogen bond. And what's a hydrogen bond? Well, it's a field. Well, what is a field? What's a force? It's energy. Those are just concepts. You can't say that it's energy, field, or force. You got to put a stick in there. What is that stick? Why is it frozen? Why is it a solid stick? Under the rope model, you can explain that. Because there is a physical object in that space between two atoms that we cannot see or touch. Okay, so let's do another experiment. This is a thought experiment, okay, for you to ponder. It's got to do with temperature, but in a different way, okay? And here it is. Here we take air, okay, and we're going to squeeze this air. Air is transparent. We're going to squeeze it now, okay? We're going to compress it. Same amount of air, but in a smaller volume. Does it become opaque? And when we release it, and the air can now expand again in the volume, right? Does it become transparent? This is a million-dollar question, okay? And unfortunately, well, I don't know if unfortunately, but quantum mechanics cannot explain that at all. And here, let me show you an example, okay? And this is for you to ponder about anyone who's got a PhD in mathematical physics, okay? Here you see their answer after over 200 years that we've known about gases and their relationship to pressure and to temperature. Okay, and here you have two testimonies. There were a lot more, by the way. Okay, you can look them up on your own. But one site, it's a professional site that sells cooling equipment, says pressure multiplied by volume divided by temperature equals a constant. The combination law, that's Boyle's law, okay, Robert Boyle, and Charles' law, okay, there you have them, the equations, explains what happens to air when it is compressed into a smaller volume. Okay? It tells us that when air is compressed, the pressure and temperature, right, of the air increases. We have higher temperature, according to this fellow, right, or this site, as the volume of space containing air decreases. By pushing air into a smaller space, we force it to become hotter, okay, and more pressurized. What does the famous stack exchange say? It says exactly the opposite. Okay? It says, in an ideal gas, there is no temperature change upon compression or expansion. The only gases that come close to being ideal at room temperature are helium, hydrogen, and neon. They actually slightly cool on compression and heat on expansion at room temperature. And if you go to the Stack Exchange to look up that, you'll find at least 5 different answers from all these great PhDs and master's degrees in physics, mathematical physics, and they all contradict each other. And the punchline or the icing on the cake is that the Stack Exchange says the question is not finished, the question is still open for anyone who wants to answer. So why don't you go there and tell them that they're all a bunch of, well, I'll withhold my opinion on that. I mean, if after 200 years, quantum cannot unambiguously tell you whether temperature goes up when you compress, if we have all these PhDs and master's degree in mathematical physics, and they all still have just opinions, there's no unanimity, not everyone thinks exactly the same way on this issue after 200 years, then you should start questioning those people who have PhDs in mathematical physics. Okay, what did they study? Or what did they memorize, really? Okay, So all I can do is do the same experiment I just did, the thought experiment, and I'm going to do it in space this time around so that there is no loss of heat to environment and all that nonsense that they bring out. Okay, so here we do it in space. Okay, we're going to compress air in a box somehow in space, and the same volume of air is not allowed to escape, and we just compress it into a smaller volume. The question is, will it become opaque when it's compressed? Will it become transparent when it comes out? What's your guess? Okay, so again, food for thought. And a lot of people say, well, Bill, tell us the answer. Really, it's better not to give you answers. It's better for you to start thinking about all these things, because if I give you the answer, all you did was memorize like all these people did in college. They went out there, they memorized whatever they were told, and they just repeat, they parrot whatever they've got. They've got all this logic to back them up. And then you catch them at the stack exchange, they all have different opinions. So this guy went to Harvard, the other guy went to Cambridge, and this guy said, no, I learned that the temperature goes down. The other guy said, no, the temperature goes up. After 200 years, they still can't reach an agreement. That's unbelievable. It's really incredible. Okay, so people are probably going to answer that next comments, and I'm sure they're just going to give their opinion. That's all they're going to give. And everyone's going to have a justification for their opinion. The question is that after 200 years, we still have no solid answer that everybody on earth agrees to. You would think that on this issue they would all agree, because after 200 years we should know whether the temperature goes up or down. And they don't. They all have opinions. That's what's incredible. Okay, so here are my conclusions. Quantum particles are not corpuscles. Okay, let's make sure we understand that. Corpuscles belong to classical mechanics. Okay, quantum particles are not particles. They use the word particles to mislead. And when you put them against the wall, they tell you, well, they're not really particles. So what are they? What are particles? You have to take 10 years of mathematics at the university to understand what a particle is. That's the answer. Okay? So particles are not particles. They represent them, when they give you a physical interpretation, they represent them with balls, with little dots or whatever. But when you put them against the wall, they say, oh, those are mathematical, wave function collapses? Is that what they are? A field collapse or whatever? Quantum waves are concepts. They're moving vectors. There is no physical object called a wave. Wave is not only a verb, but it's an irrational verb, because what they're moving are magnitudes and directions. They're moving numbers, and that is very scary. Quantum mechanics cannot explain transparency or opacity with one-way mechanisms, even if we concede what these people are saying. They're saying that all these particles or waves are going through the wall, whatever wall, it doesn't matter. They're saying whether it's a wall of air, wall of water, wall of glass, or wall of bricks, they're saying that it goes through the wall. In fact, you just had a couple people say there that their waves come through the wall and feed their computers, their Wi-Fi or whatever. So the wave goes through the wall. The part of I guess that's when they talk about waves, because everybody said, well, yeah, I can imagine a wave going through a wall. Can a particle go through a wall? I mean, are we talking about photons? Particles of light going through the wall? Is that what's going through the wall? So that's when they switch over to wave. And of course, you won't find the wave in the standard model of particles. What you'll find is particles. No waves in there. Never find a wave in there. Wave is something that belongs to James Maxwell, 19th century. They only introduce it when they can't explain it with particles, or when they want to mislead you and say, well, here's the physical interpretation, we do it with waves. Because how else are you going to explain, for example, the verified wave nature of light? You can't do that with particle. Is the particle moving up or down? Up and down, I mean. Why is it moving up? What's pushing it up? Why is it moving down? So that's when they introduce the wave, and they say, well, the wave, you know what a wave is. It just goes up and down. Well, what's going up and down? And the answer of most mathematical physics is nothing. Nothing is moving up and down. That's the answer. Okay, we identified 3 clues. One is alignment. Okay, the polarized lenses. Okay, that's one way Mother Nature distinguishes between opacity and transparency. Another one is quantity. We put more quantities of something, and what was transparent, you put all these transparents one next to the other, and you turn it into opaque. And if you want to turn opaque into transparent, maybe you just got to make it thinner, right? Maybe you have to align it, and now it becomes transparent. A piece of cheese, you can take a block of cheese, well, it's probably opaque, okay? But if you make it thin enough, I mean, if you could make it 1 atom thin, maybe you could see through it. Huh? Could it be? Okay, and then the other one that we discussed today is temperature. Okay, whatever temperature is, apparently it's something to do with frequency, with wavelength. Okay, that's probably what temperature has something to do with, maybe with the vibration of molecules, which in turn affect the ropes that interconnect the atoms and molecules, right? And so apparently temperature also is a way Mother Nature converts opaque into transparent and transparent into opaque. Okay? Food for thought.